Yeah, excuse me, ma'am. I'm trying to make this batteries.
Today. I don't know what I did. I mean, that's just not anybody get hurt? Yeah, you usual suspect.
Yeah, that's gonna say why you used to.
Tomorrow.
Dr. Pettis, can you hear us?
Loud and clear.
Great. All right, so I think we have everybody here. Certainly the important people are here. The family, right? The most important people for Mattias and his success. So, and then the second most important people are his committee then evaluating him. So, it's my pleasure to welcome you to Mattias Turner's PhD defense. To give you a little bit of background on Mattias, he's an Aggie all the way, and we're certainly the better off for that. He got his bachelor's degree in mechanical engineering at Texas A&M in 2017. Got his master's degree in 2019. But I will mention that he's been doing research with our group since he was an undergraduate student. So his last year as an undergraduate student, he was working in our research laboratory. So basically since the 2016, he's been with the group. So he's been here a long time. So I think the work that you're going to see here is a cumulative level of knowledge, right, that's gone into then what I think is some really nice work that he's going to be presenting to us. So in addition to the work that you're going to see here, we also like to say, at least for the PhD students, that he's been quite successful. So in total, he has at least 11 published journal papers and one more that's been submitted and a couple more that I think that will come from this defense, and as well as 24 conference papers in his graduate group. So what we're going to see today is some of the recent work that he's been doing with respect to the detailed measurement of laminar flames, focusing on, so to speak, the flame thickness, which he'll tell you it's incredibly hard to measure, and basically nobody's really done it before until Mattias is going to show us how to do it here.
Thank you very much, Dr. Peterson. Yeah, like you said, I've been here for quite a while. This will be my 11th year at A&M, and I think 6 or 7 years in this research group, and I have loved every minute of it. I would like to thank the committee for being here and reviewing all of my work and for your guidance and support over the years, especially Dr. K and Dr. Peterson. You guys have definitely been involved from day one with a lot of the stuff that we'll see here today. So without further ado, let me here. I would like to start with some acknowledgements for some of the students who have kind of helped me along the way. The flame thickness concept and some of the initial work that we did was actually came out of some of my master's work that I did alongside Tyler Pascal. And the flame thickness kind of routine measurement was initially his idea, and he did a lot of the initial work, and I've built on that. And then for the experimental setup, this would be stuff like setting up the high-speed camera, which actually is kind of under the jurisdiction of Dr. Kalaiolaka. Matt Hay, Tyler Pascal, and Pradeep Parajuli, those 3 students were in Dr. K's group, and they have, over the years, really been very helpful in setting up all of these systems. And then Anibal, he actually designed and built the rig that I used for this, and a lot of his design decisions have helped me immensely along the way. So the rest of the work is mine. So just to give a little bit of an outline, I'll start with an introduction, kind of introduce the flame thickness idea, and look at flame propagation, what happens as a flame propagates and becomes unstable, and how that changes flame propagation. We'll look at the experimental tool that we used, and then I'll look into the flame instabilities and kind of describe how those work and how they rely on how they're affected by flame thickness. And then I'll go into the flame thickness measurements and talk about some future work. So to start off with some background, why does any of this matter? So when designing a combustion system, we need to know how fast combustion will happen and how long, both in time and in space, it takes for combustion to occur. So there's, in any kind of engine or combustion system, there's a lot of processes that have to happen. Listed here, fuel injection, things have to mix. We need to get to stoichiometry, more or less. And then the flame has to propagate and burn all of our reactants to release heat and get us the useful work that we need. The amount of time that takes should roughly match how much time or space is given in the system. So we need to know how fast things occur so we can design systems to work well. And just some of the length scales here, we're talking about centimeters to meters, inches to feet, and then some of the time scales here, basically on the order of milliseconds overall. Some of the combustion processes take place over microseconds, but overall we have milliseconds for these things to happen. So really, really fast processes, which means we need high-speed cameras, basically. So with that in mind, we need to be looking at flame propagation. And so that's kind of where all this is coming from. We're going to be looking at flame propagation, the rates that that requires, and the things that affect how fast flames propagate. So I kind of broke it up into some really general concepts here. The things that affect flame propagation rate are basically chemistry, thermodynamics, transport, and then fluid mechanics we'll talk about in a minute. Chemistry, thermo, and transport, these can be modeled in a one-dimensional way, which is relatively simple. We like one-dimensional models. They're easy, fast, relatively speaking. It gets more complicated when you talk about fluid dynamics, turbulence, things that basically you have to account for multiple dimensions. You can't model turbulence in one dimension. 2 dimensions, we can get somewhere. 3 dimensions is real, but that takes an immense amount of computational effort. And then when you combine 3-dimensional turbulence with chemistry and the rest of these things, we get chemical reactive CFD, which is kind of the holy grail of combustion research. So flame instabilities. Just because a flame is laminar does not mean it's necessarily propagating at a steady, stable, constant rate. What I have here are some videos of different kind of flame morphologies. I'll explain, where I get these images, but basically these are spherically expanding flames from our experimental setup. And this first flame here that's propagating, this is what we call a stable, just a smooth laminar flame. This is kind of a typical experiment. This flame, as it propagates out from the center gap there, that's a spark gap. As it propagates, it's smooth. There's very few wrinkles. And this is really nice for measuring laminar flame speed. It's nice and smooth. But sometimes things like the hydrodynamic instability set in, and we get wrinkles like this. If you look closely, you may be able to see there are cells on this flame. There's little bubbles that kind of form on the surface. And all these wrinkles basically increase the surface area and cause the flame to propagate much faster than under the smooth laminar case. This is an example of the hydrodynamic instability caused by thermal expansion of the hot burned gas inside the flame. It's pushing out against the flame front, basically faster than the flame can propagate, and it causes these wrinkles. This is driven by a density change. There's also a thermal diffusive instability, and this is driven by diffusion of heat and mass. And when those things are imbalanced, we get these little bitty cells on this side. So this is another flame that had this thermal diffusive instability, and they look entirely different. The perturbations on the flame front on this flame are much, much smaller because they're driven by a molecular process. This is on the cells, or the instabilities on the order of the flame thickness scale. So we're talking about microns and maybe even smaller. The other one, the hydrodynamic instability, when we're just looking at that can be centimeters or millimeters, so relatively larger. These things can happen at the same time. So this flame down here actually has both the hydrodynamic instability and the thermal diffusive instability kind of working together, and they play off of each other. There's another instability, the buoyancy instability, and that's this flame at the bottom right, where the flame is propagating basically so slowly that the hot gas floats and causes the flame to burn up simply just from the hot gas floating. We're not talking about this one because it's slow flames, and basically all the flames that I studied for this particular study were fast enough to not be affected by buoyancy. So again, the reason why these things matter is because cellularity, that's instability, it changes the fundamental flame propagation rate. It changes the rate that flames propagate, and it causes the flame to accelerate. It's kind of a type of turbulence, so it's a fluid mechanic process, but it's not necessarily a Reynolds number flow-based turbulence. And this was kind of characterized by George Markstein back in the early 50s and late 40s, actually. We use a spherically expanding flame setup. It has a lot of advantages, mostly due to the fact that inside the rig, it's a constant volume, closed chamber, and we can control the fluid flow very well. So for a laminar experiment, the gas isn't moving. So we don't have any of the problems that come with a Bunsen burner or other types of flame of burners that have to deal with the flow of the gas through the burner. There's no flow here. And all the experiments here I'll show are laminar. This is just kind of an example of one of the measurements we can take. I'm not going to talk about this in too much detail, aside from the fact to show that we have flame propagation speed on the vertical axis. And as the flame propagates from right to left, when the instability sets in, the speed picks up significantly. So we can really, it's very sensitive. Our measurements are very sensitive to the flame speed, and we can track that very quickly, very easily. So just a little bit of literature review on some of the fundamental research on that kind of started this instability field. Derieux and Landau in the late 30s, early 40s, independently but simultaneously came up with an instability, basically a proof to show that flat planar flames, which are kind of a one-dimensional idealized flame, they are inherently unstable when a perturbation is applied to the flame that is greater than the flame thickness. Their model was relatively simple. It didn't account for flame structure, so the flame had no thickness. It was simply a kind of a demarcation between the unburned reactants and the burned products, which meant that it was invalid for small wavelength disturbances on the scale of flame thickness because it couldn't resolve that. So Markstein kind of built on that and did a lot of experiments that showed that the instabilities are controlled by pressure and fuel molecular weight, which are essentially proxies for pressure being flame thickness and fuel molecular weight being thermal and mass diffusion, so the Lewis number. I'll explain those in a little bit. And he came up with a curvature correlation, essentially, that shows that when we have a curved flame, that actually helps stabilize the flame. So we have a curved flame here. That's our spherically expanding flame. Curved flame front is actually more stable than a flat flame front to these instabilities. And then about 20 years later, some of the Soviet researchers actually came up with a spherically expanding flame model. So all the stuff before the late 60s was built on a one-dimensional flat flame. And there were things built on that, but essentially this was the first spherically expanding flame model in the late 60s that took into account Markstein's curvature effect. So then fast forward another 20 years, and some researchers at Northwestern University in Illinois, specifically Moshe Matalon, he built a model that predicts the onset of these instabilities. And it takes into account thermal diffusion, mass diffusion, the hydrodynamic instability, and essentially combines all of these effects on a spherically expanding flame and shows how these instabilities will grow with time. There were some kind of assumptions, some drawbacks made with the initial model in the late 80s that basically didn't take into account certain aspects, but then about 15 years later, they developed some modifications that took into account temperature dependence of things inside the flame, different properties of the gas, transport properties, and then a stoichiometry effect for the Lewis number, because the thermal diffusion and mass diffusion rates are controlled by which reactant is deficient. So if you have a lean mixture, we're fuel deficient, and that means that that's the controlling species. So one kind of key aspect of this model is that historically it tends to underpredict the critical flame size for instability. So what the model does is essentially predicts how big the flame has to be for the instability to set in. And this is one of their most recent works. This is a paper from Professor Mattias. Their experiments are shown here in these kind of black points here. This is the critical radius of the flame, so the flame size at which the instability sets in. And then the model down here in red, it underpredicts what the experiments show. And this is relatively recent. And this is relatively simple mixture. It's just hydrogen air, rich, a little bit of heating, a range of pressures, but it just consistently underpredicts the critical flame size. Now, like I said, the flame thickness can account for the effective pressure. This is one of the things that George Markstein kind of figured out. This is some data from Princeton that shows the critical radius for the instability onset for some acetylene flames at a range of pressures. I don't have them listed here, but basically each of these different points represents a different pressure. They went from, I think, 4 atmospheres up to 10 atmospheres of initial pressure. And they're kind of all over the place, but the trend is that a lower pressure flame goes unstable later. It's stable for longer. So as pressure increases, the critical radius drops. But if we normalize the flame size by the flame thickness, all of these points fall on top of each other. So these points on the left, I've represented in green in the plot on the right. And this is the critical Peclet number. So the Peclet number is the flame radius, flame size, normalized by the flame thickness. So Peclet numbers are essentially flame thicknesses. And what this shows is that acetylene flames go unstable at about 400 flame thicknesses. When the flame gets to be 400 times its thickness, the instability sets in. And I took some data several years ago, the blue points here at a lower pressure, and showed that we are in agreement with what's there in the literature. But you need the flame thickness to get this Peclet number to accomplish this normalization. And so we'll get into all of the things that implies. But yeah, how do we get flame thickness? How do we measure it? We can predict it, and I'll talk about some of that as the presentation goes on. So we can measure it. There are ways to measure flame thickness, and this plot here on the right are some Schlieren interferometry measurements in the early 70s from Derek Bradley at the University of Leeds. They measured flame thickness for some methane air flames, and basically showed that the flame thickness from their measurement ranges from 1 to 10 millimeters, which is relatively large. There's a definition of flame thickness that they've called the laminar flame thickness, which is essentially the ratio of kinematic viscosity to flame speed. So it's a relationship between viscosity or momentum diffusivity and convection. And this laminar flame speed predicts a flame thickness of between 40 and 200 microns. But their measurement is millimeters, orders of magnitude greater. So we're talking about 25 to 50 laminar flame thicknesses. And then this is some more literature data here from several groups. Dr. Bradley has done a lot of flame thickness measurements over the years. But essentially all of the data here show that measured flame thicknesses are always significantly greater than what's predicted by theory. Conversely, theory always underpredicts measured flame thicknesses. So what this means is that the theory doesn't really pick up what's happening inside the flame. And maybe the definitions aren't lining up, and I'll get into that. But to kind of explore that, we need to figure out what happens inside the flame. So here on the right, I have kind of a schematic of a flame. It's a propagating wave. The flame being this kind of red zone. And if you kind of imagine a flame propagating in space through a cloud of reactants, and as it propagates from right to left here, the burned products are on the right, high temperature, low density product gases propagating into the reactant mixture, which is fuel and air, fuel and oxidizer at low temperature, high density. A lot of things happen inside the flame. Generally speaking, I'm really not giving chemical kinetics its due diligence, I guess, here. But inside the flame, we have a lot of heat release, temperature rise. There's a lot of species changes, a lot of chemistry that goes on, which we model using chemical kinetics. I have kind of a global reaction for methane and oxygen becoming CO2 and water. This is very general. And this is kind of the carbon pathway there. Some of the major reactions that control global combustion rates, like flame speed, are given here. And these are really well-known, well-studied reactions. With a model that takes into account all of the chemistry that goes on inside a flame, or that we hope, models all the chemistry that goes on inside the flame, we can get predictions of the temperature profile and many other physical parameters of the flame. So here I have some model predictions for a methane air flame. The blue curve is the temperature profile. So we kind of zoom in on the flame and look at what's going on inside there. This blue curve is the temperature profile. So we go from room temperature up to about 2000 kelvins, which is north of 3100 degrees Fahrenheit. And there's a steep change in temperature here in the middle. And then there's a lot of chemistry, of species creation and destruction that goes on inside there. I have some just kind of notional curves for some intermediate radicals here. This being CH and OH. These are very commonly studied combustion species that we can model. These things are created in the flame and then destroyed. They don't exist in the reactants or in the products, more or less. So they're what we call intermediate species. This is modeled using kinetics mechanisms, chemical kinetics mechanisms. They can range in size from 10 species to well over 1,000 species. Tens of reactions to tens of thousands of reactions for the really, really big ones. The one I'll be using mostly in this presentation is Aramco MEG 1.3, just because I'm looking at relatively small fuel molecules, methane, propane. I looked at some syngas mixtures as well, but this is kind of a mid-range, as far as size goes, mechanism with about 250 species and 1,500 reactions. And this can be run on PC. You can calculate flame thickness using this in 10 minutes for one condition. It does take some time. So we've looked at what goes on inside a flame. Now let's characterize the thickness. How much space does that take? This is a paper from the 80s from Jarenczynski. This red curve is the temperature profile, like I showed in the last plot, but in red now. And then this is, again, intermediate species or maybe heat release or just chemical activity. And we can characterize different formulations of flame thickness. So one of the really common ones is the thermal gradient thickness. We can look at how wide the temperature profile is, how much space it takes for the temperature to go from room temperature to flame temperature. And this is characterized or kind of estimated by this thermal gradient thickness, which essentially takes the steepest slope here, which is this black line here. We take that steepest slope and then extrapolate to the burned gas temperature and the unburned gas temperature, and that distance is what we call the thermal gradient thickness. And that's shown here by D delta T down here. And one thing I'd like to point out is that this thermal thickness does not really actually take into account the full flame. So if we want to, conceptually say flame thickness is the distance it takes to go from reactant equilibrium to product equilibrium, we're talking about a distance from out here all the way out here. But this thermal gradient thickness kind of estimates that to be this smaller thickness. And as I'll show, this is actually one of the largest flame thickness definitions out there, which is surprising. There's also a Zeldovich thickness, which kind of, it's a ratio of thermal diffusion to convection. And it's tough to pin down, where this thickness is kind of centered in the flame, but that's shown by DZ. I should say, we have to get a temperature profile to the temperature gradient. We need a temperature profile somehow. So we can model it, we can measure it, maybe. I'll get into that. There's also this kind of diffusion thickness, which is a ratio of thermal diffusion to convection. And that's usually calculated from the reactant properties of thermal conductivity, density, specific heat. But we need to pick a place to analyze these things because these are temperature dependent properties. The temperature is changing rapidly throughout the flame. So depending on where you choose to be, where you choose to evaluate these properties can affect what that definition gives you, what that thickness is. So there's some drawbacks to that. There's also other ways to characterize the flame. There's many other things that are changing. There's species being created and destroyed. Heat release, we can look at viscosity changes. There's a density change that happens. And then that laminar flame thickness that I talked about is the viscosity definition that a lot of people use. Just to give you an idea of the scale of these thicknesses and different definitions and what the difference between those things are. This is a syngas flame. I'll talk about the gases later, but essentially this top curve is the thermal gradient thickness. This bottom curve is that Zeldovich thickness that I talked about. For the same flame, the same exact flame, these two definitions give very different flame thickness results. And then I kind of came up with, I calculated a density gradient thickness that's essentially the same definition as the thermal gradient thickness, but applied to the density profile. And that lands kind of somewhere in the middle. The reason I looked at this density gradient is because the hydrodynamic instability is driven by the density change. So if we want to look at how the flame thickness affects the hydrodynamic instability, we should probably look at how the density is changing throughout the flame. So that's where this definition comes from. I also like to point out that the scale that we're talking about here is tens of microns, maybe up to 100 to 200 microns. This is a high pressure flame, so we're talking about 10 atmospheres. So these are relatively low flame thicknesses compared to some of the stuff we'll see later. Now, like I said, there are species that are changing throughout the flame, and we can look at those profiles and kind of and get a thickness of that profile. So this is the same plot as before. We have CH star and OH star. These species, we can look at the full width at half max thickness. So we normalize these things and then look at the half max thickness and get that as the full width at half max thickness. This can be taken from kinetics predictions. We can model these relatively quickly. But as I'll show, we can actually measure this as well. We can use chemiluminescence imaging and look at the light emitted from the flame. Each of these molecules emits very characteristic wavelengths of light, which occur for OH star, there's a characteristic feature at 307 nanometers, which is in the UV. You can't see this with the naked eye, but the cameras can look at this. And then CH star emission happens at about 431 nanometers, which is blue, which is why this flame looks blue. This is a phone video that I took from one of my experiments. And it was so cool to look at this and see that's CH star. That's exactly what we're imaging in the experiments that I'll show later. And then these are some of the reactions that occur that form these molecules. So OH star formation is shown here. And there's other reactions that go into forming, destroying these molecules, or at least causing them to emit light or convert them to some other molecules. Same thing with CH star over here. And I'd like to point out that previous students in this group with Dr. Peterson have actually done a lot of work on building these models for chemical kinetics for excited species, specifically Joel Hall and Jaap de Vries.
What's the frame rate of that movie?
About 180 frames per second. It's just,
Your camera.
yeah, that's my phone. Played back at 30 frames per second, so it's about 1/6 regular speed. This is just some flame thickness results. So if we model OH star and CH star for methane flames, and then look at the thickness from those kinetics predictions, this is the kind of result that we get. So here on the left, this is comparing CH star and OH star profile thicknesses for 1 atmosphere, room temperature, methane air flames. And we see that on the lean side, CH star and OH star, those profiles are pretty much the same thickness. And then on the rich side, as we get more and more fuel, there's more CH star, there's more carbon, so we get more CH star, and that thickness increases over the OH star thickness. And then over here on the right, I'm showing the effect of pressure on CH star thickness, basically showing that for increasing pressure from black to red to blue, we go from 1/2 an atmosphere to 1 atmosphere to 5 atmospheres. Pressure causes flame thickness to decrease significantly. So to summarize where we are so far, flame thickness and flame instability are tied. Flame stability affects the propagation rate of a flame in ways that are not really necessarily well known at this point. The leading model for predicting the onset of instability tends to underpredict when the instability will happen, which means it will overpredict flame propagation rates in a greater sense. And then measuring flame thickness, measured flame thicknesses tend to be underpredicted by theory by about an order of magnitude or more. However, there are different flame thickness formulations, and that can have an effect. So it could be that we're measuring something that we're not, the theory is for something other than what we're measuring. You know, if we're measuring a Schlieren interferometry measurement, that's a density-based measurement. So it doesn't really make sense to use, say, a viscosity flame thickness. So that's what I mean there. So to look kind of forward at my objectives for a lot of this work, I basically wanted to measure the onset of instability in a range of flames. I wanted to evaluate the model that we use for predicting that and look at the effect of different definitions of flame thickness on that model, because the flame thickness has to go into the model to compare to the experiment. You need the flame thickness to compare experiments to the model, and try to figure out what's the relevant flame thickness, that length scale. And then as far as measuring flame thickness, I wanted to use chemiluminescence imaging, look at CH star, OH star, and develop that diagnostic to get kind of a working system for measuring flame thickness. So now I'll go into all of the tools that I used for doing this, the spherically expanding flame rig, the high-speed cameras, and all of those fun tools. So this is our spherically expanding flame vessel. Some of you may have heard me refer to it as a bomb. It's an explosion chamber that holds the combustion inside. It's totally sealed. This is what Annabelle designed and built. And when I started here as an undergrad, we were actually assembling this. So I got to be here kind of at the end of his time, but help put it together and work from the ground up from the very beginning with this rig. So this has been exciting to see this thing go from being brand new to making all these measurements here. Just some characteristics here, some dimensions. On the inside of the rig, it's about 34 liters of internal volume, which is maybe about 10 gallons. It's 14 inches tall and 16 inches tall on the inside and 14 inches in diameter. It has 5-inch windows, and we have 4 windows that are perpendicular to each other. So we have 2 axes of optical access. We can look at the flame from different angles, use different cameras and things. There are fans for mixing, creating turbulence, and it's rated for an initial pressure of about 10 atmospheres. One of the optical diagnostics we can use is a Schlieren diagnostic, which essentially takes a mercury arc lamp here, which emits very bright white light. We collimate that as a 6-inch diameter beam and put that through the 5-inch diameter windows. And that light is collimated, so all the light beams are parallel to each other. And as the flame propagates through that light, it bends the light. The density gradient causes refraction, and we can measure that with the camera. Just to give some kind of reference for the numbers that I'll talk about later for the chemiluminescence camera. The Schlieren camera has a 1 microsecond exposure time, at least that's what we've used. Frame rates of 5,000 to 25,000 frames per second, and a resolution or a magnification of about 330 microns per pixel, 30 pixels per centimeter. Try to keep those numbers in mind for the next the chemiluminescence diagnostic, which is shown here with a schematic with the Schlieren diagnostic also installed at the same time. So the Schlieren is out here, kind of as U-shape, and then the chemiluminescence diagnostic is here through this window in the center. And there's a lot of pieces that go into play here. Basically, we used Photron FastCam SAZ with an intensifier, which we call the high-speed intensifier. We used gate widths from 50 to 75 microseconds here, which is much, much longer than the Schlieren. This has a gain setting, so we use 64% to 70% gain. 70% was only for a couple of experiments, Dr. K, don't worry, when the flame was really dark. And we ran this at 5,000 to about 15,000 frames per second. Now, to zoom in on the flame, we used a couple of different lenses. There's one lens that's what I'm calling the UV lens. It's a lower magnification, but it transmits in the UV and the visible, so we can look at OH star and CH star. And then we have a high magnification lens that's called the K2, and that one is made of different glass, and it only transmits in the visible. So we couldn't look at OH star with the high magnification. And then these are the optical filters that we used for OH star. These have a bandwidth of about 17 to 19 nanometers, so relatively narrow, looking at OH star and CH star emission. This is what it looks like installed in the test cell. It looks pretty messy because there's a lot of wires and things, but basically here in the center is the chemiluminescence diagnostic. We have the SAZ, the high-speed cam, the intensifier, and then the lens system, which is quite long, sitting right here. And then out here is the Schlieren diagnostic, which has the mercury arc lamp collimated through the windows and out to the Schlieren camera. For the chemiluminescence camera, we need a way of, excuse me. We need a way of getting a scale from pixels to distance. For the Schlieren camera, we have the windows. Those are 5 inches in diameter. That's a very well-known dimension. And so we have a software that gets that scale from every image. In the chemiluminescence images, we don't see the window. So we need some other way of getting the scale. So we used a US Air Force resolution target. And this is a cell phone picture that I took. This is about 1 inch in diameter. And so this little scale down here is quite small. Basically, this is a pattern of lines that are evenly separated, and these have no dimensions, and we can image that with the camera. This is what it should look like, and then this is what our camera picks up. So essentially what we do is we look at the pattern, the largest pattern that is indistinguishable and gets blurry. There's a little bit of, arbitrariness, ambiguity in picking which of these features is the largest blurry one. But let's say we pick this one down here, which is group 3, element 5. And then basically go and look up in a table what that gives us as the ultimate resolution. And for group 3, element 5, that gives us 12.7 lines per millimeter, line pairs per millimeter, I should say. The line width at that point, each of those lines is 39.4 microns wide, which means that the line and the space next to it is that width. My analysis basically says that with this setting, the blur, or kind of the bleed of the light coming out of that line, is half of this distance, because the dark area is getting overcome by kind of blur or diffraction of the light. So we have a bleed of about 20 microns. And I'll show later that actually lines up almost perfectly with the experimental uncertainty, which could be a coincidence, but I don't think it is. And then another thing here is that we got the scale for the images, like I said, from these large bars down here. These groups were 625 microns wide, and taking many average measurements from on those bars gives us 13.5 microns per pixel. This is the highest magnification setting that we used. For the other lens, the low magnification lens, we basically had the same setup, and I'll show those numbers later. So that's the experimental setup. Now we'll get into the flame instability study and look at some of the results from measuring the onset of instability. So to measure the onset of instability, we need to know the flame size. So we use an edge detection algorithm. This was built by a previous student, Travis Sykes. And essentially, from our Schlieren images, we can track flame radius and therefore the flame speed. And then we can identify which image had the first sign of the instability and mark that as the critical radius. We can track the radius in time with the frame rate of the camera. And so one thing we can do is measure radius, flame speed, and then we can also get the critical radius. And then if we know the flame thickness, or pick a flame thickness, we can get the critical Peclet number for the onset of instability. The gas mixtures that I used for this instability study were syngas mixtures. I'm not going to go too much into detail on these, but essentially there were 5 component mixtures of hydrogen, carbon monoxide, oxygen, CO2, and helium. And with all of those knobs I can turn, I can control thermal diffusion, mass diffusion, flame speed, and all sorts of things. To constrain some things, I picked the stoichiometric equivalence ratio. So all of these are phi = 1. And I controlled the dilution. So it was the same for every experiment. Every mixture had the same amount of reactants, same amount of inert gases. The mixtures don't necessarily matter that much for what I'll be talking about. But one big thing I want to point out is that because these have so much helium in them, the Lewis number is always above 1, which means that from a thermal diffusion standpoint, the thermal diffusive instability is entirely suppressed. So these flames will only exhibit hydrodynamic instability, which is still affected by thermal diffusion. But the onset of instability that I'll be measuring here is essentially always hydrodynamic. And that's what these look like here in this video. So as the flame propagates in this video, we can kind of say right about here is where the instability sets in. And for each experiment, I look through and pick that and then develop an uncertainty from that based on, the instability kind of fades in over time. So there's a range of frames that you could say the instability starts in. So that gives us an experimental uncertainty. So this is the critical radius results from this study. We can kind of see these uncertainty bars being the range of frames that I was talking about. And basically what we're seeing is that with these mixtures, the critical radius ranges from about 1 centimeter up to 6.5 centimeters. This flame right here happened to go unstable right before the edge of the windows. So that was kind of convenient. There are two mixtures here that I wasn't able to study at higher CO2 dilutions because they were too slow and had the buoyancy instability. And when that sets in, it kind of changes the whole dynamic. So I didn't analyze those for this instability. But the uncertainty there is about 0.1 centimeters based on the uncertainty in the frame that we're choosing. One thing we're seeing here also is that the instability onset is not really dependent on the CO2 mole fraction, which is some kind of interesting. It's more controlled by the amount of hydrogen in the mixture. And this is because hydrogen, two things. One, hydrogen is, since it's such a small molecule, it diffuses really quickly, which makes things unstable. And it also creates a thinner flame, which both of those things, a lower Lewis number and a lower flame thickness, both cause instability to set in earlier. So these high hydrogen mixtures have a low critical radius, low hydrogen, high critical radius. Now, the model for this predicts the Peclet number. It doesn't predict radius. So you have to pick a flame thickness to compare between the two. So at first I looked at taking the experiment, dividing by flame thickness, because we measure the flame radius, divide by flame thickness to get a Peclet number, an experimental Peclet number, and compare that to what comes out of the model. And essentially what that means is we're dividing a big number by a small number, which means the number gets a lot bigger. The uncertainty for these increased significantly, it just kind of amplifies that 0.1 centimeter uncertainty onto the Peclet number scale. The uncertainty in the model is based on variability in the input parameters. I don't really have time to talk about all those different things, but essentially there are inputs to the model that must be modeled from another model. And those things have some uncertainty based on how you model them. And so those inputs give us these uncertainty bars on the model up here. What's interesting is the model overpredicts the onset of instability if we use the thermal gradient thickness or the density gradient thickness that I talked about earlier. These are kind of larger flame thicknesses. We see, first of all, the experiments lie on a relatively clean line. So these solid points here are the density, using the density gradient, the open points of the temperature gradient thickness. And we see that the experiments, there's a nice clear trend here with Lewis number. So as Lewis number increases, flame is more stable. But the model overpredicts the onset of instability when we use this flame thickness. Now, the model was designed to use the Zeldovich thickness, which is much smaller. If you remember that plot kind of at the beginning where I had the thermal gradient thickness, the Zeldovich thickness is much smaller than that, which means that the experimental Peclet numbers are much, much larger. Now, if we use that, the experimental uncertainty is amplified through the roof. And now the model tends to underpredict, which is kind of more in line with what we see historically. There's some coincidental agreement down here, but that's just kind of happenstance, I think, because these trends do not line up at all. Now, I wanted to look at it the other way around. The experiment, we measure the critical flame radius. Now let's take the model and fit it to the experiment. That's what we should be doing. So instead of converting flame radius, I'm going to convert the Peclet number from the model, multiply it by the flame thickness to get the flame radius. And that's what I'm showing here. This on the vertical axis, we have the predicted critical radius from the model against the experimental critical radius. This black line is kind of the line of agreement. Ideally, if the model was perfect, all the points would lie along this line. The different flame thickness definitions that I use to convert the model predictions are shown in different colors. Zeldovich thickness is in blue, density thickness in red, and temperature thickness in black. And this kind of essentially lines up with what I just showed before. The Zeldovich thickness causes the model to underpredict the experimental data, and then the other two thickness definitions results in the model overpredicting the experimental radius. However, using a density profile thickness these trends, the slope here is very close to a slope of 1. So what that means is the model seems to be grabbing the trend well, but the magnitude is off. And for this case down here, there's these squares and dashed lines. This is a case with no CO2. This was a syngas flame that was just hydrogen, CO, oxygen, and helium. And in that case, the model, that was kind of the case where the model performed the best. However, that only 1 centimeter of overprediction was anywhere between 17 to 100% of an overprediction. So when we look at it in that way, the model still isn't doing that well, but that was kind of the best case for this model. And so kind of because of this, I think the density profile thickness may be the way to go because the trends are matching, but the magnitude is still way off. And essentially what that means is the model needs more steady. And that's kind of the summary here. The model, this Madelon model requires flame thickness to convert from the model output to the experiment. Choosing different definitions of flame thickness kind of give us different results, but there's no consensus on what that flame thickness should be. And if we try to look at a hydrodynamic instability or a hydrodynamic flame length scale, density is probably the way to go, although the model still needs a lot more work, which I think is basically what we need is more experiments to get a correlation to fit the model to it and see where the model can be off in other ways. But that leads us into the flame thickness study. So can we measure flame thickness? And basically, are our modeled flame thicknesses accurate? We need to use a model to get flame thickness for these other things. So now we're going to talk about the flame thickness measurements, which were driven by the chemiluminescence. So on the left here, these are the lower magnification settings and a sample video. A couple things I want to point out. First of all, for the lower magnification lens, again, it transmits in the UV, so we can look at OH star and CH star. It's because it's not as magnified, we can look at the full flame. So it's kind of zoomed out. And because of that, we can actually measure laminar flame speed. We can see the full flame and use our edge detection to measure laminar flame speed. And that was the topic of my master's thesis back in 2019. From this, basically this part of the study, because we do OH star, we looked at lean, stoichiometric, and rich. We looked at methane air flames at 1 atmosphere. Now, if we use a higher magnification lens, this is the K2 lens, we can only look at CH star. However, that's not necessarily a big drawback. I looked at a wider range of conditions, so I looked at methane and propane flames at a range of pressures from below atmospheric pressure to twice atmospheric pressure, and then looked at CH star. And then this is kind of a sample of the images. They're zoomed in, so we can only see a portion of the flame, but this is actually the way to go for flame thickness. We can zoom in and isolate the flame front that way. However, we need a way to correct for the line of sight integration because we're looking at light emitted from the full volume of the flame. The camera's going to pick up all of that emission. But we're only interested in the flame front. So we have to correct for that. And the auto transform is commonly used for this. And this is kind of an example of the process. It requires symmetry. So we take our raw images and then center them and make sure we have symmetry about the origin or cylindrical symmetry. And then this is the auto-transformed result here on the right. And essentially we can see that all of the light from the burned gas in the middle of the flame is kind of taken away and really isolates that leading edge of the flame front. There's some noise in the middle, but we essentially don't analyze that and we're only looking at the flame front, so this noise in the middle doesn't affect the measurement. So these images are the low magnification, but our high magnification images zoom in and look at that portion of the flame. And in the interest of time, I'm not going to talk about kind of the differences really between those two, the way that we analyze those, because in the end, it's the same. We're looking at a horizontal intensity profile. So this is an example, auto-transformed high magnification image. This kind of bright line through the middle of it, I did that. That's my way of showing these are the pixels that I interrogated and I sampled the intensities from. We take a measurement across the flame, and then that gives us this normalized intensity profile over here. So as we go from left to right, the intensity slowly increases, and then right at the flame front, clearly that's where all the action is. So from that profile, we can look at the full width at half max thickness, And in that case, we get something on the order of a couple of millimeters for this case. We can do that for every image in the experiment. So over the experiment, we take, anywhere from 30, 40, 50 to a couple hundred images, depending on the flame speed and other things, frame rate of the camera. And so we can track flame thickness in time with flame radius and other things. So this is an example of one of the low magnification measurements that we took. And at that time, so this is relatively low magnification. At that time, we were seeing that the flame thickness was increasing with time. So as the flame propagates and as we're taking these images, the flame looks like it's getting bigger, thicker and thicker and thicker, even though in the experiment, the flame really shouldn't be changing that much. The flame speed may be increasing a little bit because the curvature is changing. But what this meant was we were probably seeing a stretch effect. As the curvature changes, the flame thickness changes. So I kind of ran with that and did a stretch correction and essentially extrapolated to a condition of zero stretch, which gives us the flat planar flame. And for those experiments, those data are shown here. So these points up here are the low magnification results. So in blue, we have OH star and red CH star thickness. These are all for methane air at the low magnification. And essentially what this shows is that as we zoom in, so we basically with the same lens, zoomed closer and closer in on the flame. And as we zoom in, the apparent measured flame thickness decreases significantly for the exact same conditions. And I applied the stretch correction to account for the effect of that flame thickness increase over the course of the experiment. And I did that for all of these, but I just demonstrate it here on the right for the most zoomed in case. Comparing to the model predictions for CH star and OH star flame thickness. And the stretch correction tends to give us a higher flame thickness. Uncorrected, I just took the average of all of the flame thicknesses across that experiment. And at this magnification, we basically saw that we're on the scale, we're on the order of the flame thickness from the model prediction. But the scatter that we're seeing and the effect of magnification meant that there needed to be some more work done. So to kind of quantify the effect of magnification, I built a discretization algorithm that essentially maps the kinetics profile, which is more or less continuous and smooth. It maps that onto the scale of the camera sensor. So here on the left, these are the low magnification settings. And essentially, if we had this black CH star profile from flame, and then looked at it through a camera that had this pixel spacing, we would get these points. So with the red kind of lowest magnification, what that shows us is that the entire flame ends up being kind of lands on 2 pixels. As we zoom in to the highest kind of low magnification setting, the flame ends up being resolved by maybe 6 to 8 pixels, which is getting closer. But one big point that I want to point out here is that we miss the peak, first of all, no matter what. And the other thing is that if we go and say we take this red profile and we take a full width at half max thickness, that's going to give us a flame thickness that is significantly larger than the model prediction. So the model isn't necessarily right, but if the model is, the experiment's not going to catch it. The experiment will miss that result. So with the new lens, much higher magnification, zoomed in a lot more with 13.5 microns per pixel, we get many, many more pixels across the flame. We can really resolve that, that profile. So that's what I'm showing here on the right with a high magnification with, we're on the order of 20 pixels per flame thickness. And this changes depending on the flame thickness. So if we have a really thin flame, we're not going to be able to get as many pixels in there and resolve the structure, and we're back to the problem on the left. So thin flames require more magnification. Now, a little bit of kind of back to experimental setup just to show with the chemiluminescence diagnostic installed at the same time as the Spherical diagnostic, we can image the flame from 2 points of view at the same time with 2 cameras. And so with the Schlieren, we can look at the full flame and track the flame propagation over the course of that full 5-inch diameter. With the chemiluminescence diagnostic, it's zoomed in on this little white box here. So the chemiluminescence video on the left is what the chemiluminescence camera sees. So this is the exact same experiment. I synchronized them. And so essentially what I'm trying to show here is that we can track things like the flame radius and flame speed with the Schlieren diagnostic, so we know what the flame's doing. And then with the chemiluminescence diagnostic, we can track the flame thickness. And it looks like the synchronization is off because that's not right. But this is a propane air flame at 2 atmospheres. It's a rich mixture. And so we can line them up like that. From those high magnification images, we apply the Abel transform and we get this red profile. So this is what we're using to get the experimental flame thickness. And for that same experiment, for one image, I just grabbed one kind of at random. We happen to get a flame thickness measurement of about 22 pixels, which is about 300 microns at this resolution. And we do that for every image in the experiment. And one encouraging thing here is we're not seeing the flame thickness change over the course of the experiment. So that apparent stretch effect or whatever was going on is probably an optical effect. We're not seeing it here at this high magnification. So I averaged the flame thickness measurements for every image across that experiment and got an average of 19.4 pixels with a standard deviation of 3. And then using statistics, we can get a 99% confidence interval of 1.5 pixels. What's, I think, a better way to look at this is using just comparing the profiles from every image and kind of lining them up. So here on the left, the gray lines are every image from that experiment. I'm looking at the profile, aligning them to the peak, and then taking the average of that with the red one. And then these uncertainty bars, these standard deviation. Now, I'm going to move quickly to kind of keep an eye on time. But basically, we average that. Now the flame is moving during the exposure time of the camera, so we have to account for the blur that happens. So with the spot here, I'm showing as the flame propagates, and over the exposure time of the camera, we have to account for that blur, and it's traveling a certain number of pixels, and we can calculate that. We have to round up by 2 because the flame isn't going to align that well with the camera. And I developed a blurring broadening algorithm that'll calculate what would happen to kinetically predicted profile if it went through the same effect that we're seeing with the experiment. I've done these on an absolute scale, which we can talk about this later. We're going to miss the peak because of blurring, but when we normalize, which is what we're doing for the experiment, they line up very well. So here on the right, the red is the experiment, the black is the pure kinetics results, but when we pass it through the experimental effect, we get the blue curve, and they line up really, really well. So what this means is we're taking into account the blurring effect accurately within the uncertainty of the experiment. We have a good certainty there. So I applied that methodology to methane air flames, propane air flames across a range of conditions. And the experimental measurements are the points here on the plots. The solid lines are the pure kinetics results. But when we use the blurring correction, we get the dashed line. And we see that really actually takes into account what's happening in the experiment. So that this point here in the middle of the propane air plot for stoichiometric condition, that point is the one I've been showing here. And we basically see that we have to take into account the blurring to really model what's going on in the experiment. We can model the kinetics and we can model the broadening, put those together, and it lines up with the experiment very, very well. I'm going to kind of skip over this because we're running out of time, but I developed an algorithm for the blurring and it correlates very, very well. There is a way potentially to estimate flame thickness from a blurry image using this, but we'll talk about that later. So basically to conclude, this flame thickness technique works very well for these mixtures. We can model the blurring very well. The kinetics, I picked mixtures where the kinetics are relatively well known, so we have some certainty in the modeled OH star and CH star. In the future, this kind of I need to do some work on cleaning up the analysis and kind of streamlining it. I have 5 or 6 separate codes that analyze these things. But one of the really valuable things here is that we can apply this to new experiments. So we can apply this to, say, ammonia flames, or if we get new optics that transmit in the UV, we can do this with OH star. One of the drawbacks right now is that with the K2 lens, it doesn't transmit in the UV, so we can't do this for OH star. Because of that, we're limited to rich hydrocarbon flames with CH star. If we get OH star, we can look at lean flames. There's basically no CH star in lean flames. And so we're going to need to look at that, I think. And then just to kind of conclude again on the flame instabilities, the model from Mattias does not necessarily perform well. especially for these complex multi-component mixtures where there's lots of different things going on with diffusion. Normalization by flame thickness makes for cleaner theory, but it doesn't really represent what's going on in the experiment very well because of that amplification of uncertainty. And characterization of the inputs to the model need to be done. A lot of these things, the inputs to that model have to be modeled, and that causes problems. But one thing I want to point out is there's a lot of data in the literature on measuring instabilities because it's relatively easy. You just look at your images and here you go. But modeling it is much more difficult, and understanding what was going on in the experiment is also a big part of this. So I'd like to thank the committee for your time and your review and support over the years. I'd like to thank Carl, and I've actually been here long enough to know the previous facility manager, who was also very, very helpful. He taught me a lot about machining. And then the previous students that I talked about earlier, Hannibal, Travis, Tyler, Matt, Pradeep, all very, very helpful. And then I'd like to thank all of you for being here. I'm honored to have a packed room. I think this is one of the biggest defenses I've ever seen. Thank you. So, yeah.
Okay, so what we'll do for this portion, we'll entertain questions from the general audience.
I think it was a couple slides back when you were showing the experimental measurements versus the models there. It looks like they agree better at lower pressures. What effect does the pressure have there, and why does it cause a bigger disagreement as the pressure increases?
That's a good question. The lower pressure gives you a thicker flame, and basically that means we can resolve it better. We have more pixels across a thicker flame. So for those, we actually had something like 30, 35 pixels across the flame, which is more than enough to resolve what's going on. Effectively, we're not missing the peak intensity. So we get very good agreement there. One thing I will say is you may notice that over there for the propane ones, and maybe some of these methane ones, the experimental point is kind of below that dashed line and actually closer to the true kinetics. That is actually because on that particular experiment, the exposure time was less than what I modeled here. There wasn't enough time to kind of go into that, but the exposure time also has a big effect there as well.
Hi, can I ask a question from Zoom?
Thank you, Dr. Rand.
Yeah, hi. I couldn't figure out how to raise my hand on Zoom. It seems to have disappeared. But I wanted to say that the flame thickness is a very, very fundamental quantity, the laminar flame thickness in a lot of the models we need to create. And it's an input quantity. We often get it from chemical kinetics models, but sometimes these quantities don't work from chemical kinetics, so we need to get them from experiments. I came in late to your talk, but could you tell me in general how well the measurements agree with models, with these chemical kinetics models?
Yes. So the measurements agree very well with the model. However, we're modeling the excited species. Therefore, we're not necessarily being, I can't measure, the density thickness. I can't measure the temperature thickness of the flame. So when you say the laminar flame thickness, could you describe, I guess, what you mean by that particular definition?
Okay, well, when you calculate, or if you take the chemical kinetics models and you compute a laminar idealized flame burning, I guess with no curvature in effect, you measure the distance, some sort of distance between the front of the flame and the back. There's a number of ways of defining it. But the question is, and we usually pull a number out of there for the laminar flame thickness.
Okay, I understand what you mean now.
Yes, yeah, you understand. And that's a quantity we really need.
Yeah. With this measurement, because we're taking into account only the excited species, we need to look at, I guess, the relationship between the excited species profile relative to the greater flame profile.
Okay.
This profile is thinner, maybe half or a third of the full laminar flame thickness. For excited species, that profile is anywhere from a half to maybe even a quarter of the laminar flame thickness. But I think we're seeing really good agreement with the kinetics. So my intuition here is that for kinetics that are kind of well validated, the laminar flame thickness from that profile is accurate.
Thank you.
Yeah.
So my question is, when we look at your videos, it's not very clear as to when the instabilities start to show up. So can you please go again over what your criteria was for determining from your two-dimensional picture, basically, how you decide when the onset of instabilities occur?
Yeah. I'll use this one as an example. So essentially, I can slow it down and pick out the image where this happens. But right about here is where it happens. there's a kind of an ambiguous, operator uncertainty there. There's a range of maybe 5 frames. It depends on the flame. It depends on for some experiments. It was actually pretty tough to figure it out. Some of those wrinkles that happen at the beginning of the flame kind of get in the way, and it's tough to say, like, does this happen at frame 200 or frame 205? On the scale of the radius of the flame, that's not a big deal. 5 frames is not a big deal. On the scale of the Peckley number, where we're normalizing by the flame thickness, where I had those huge uncertainties, that's where that 5 to 10 frames does matter a lot. But I guess the short answer is I look at it and basically give myself a margin of error based on where it looks like it sets in. Yes.
I'll follow up on that. David actually got my question. So well done, David. Now I have to come up with a new question to add on to it. So yeah, I was wondering, had you tried some kind of Fourier transform or something to try to put some quantification? You've done this fantastic job quantifying everything else about your imaging system, but yet that one is still an operator subjective thing. Is there any way you could put some quantification on the regularity of those structures in there to set up criteria? And then as follow on to that, you've specified that your line pairs per millimeters is like 20 microns. And so what sort of limitation could the imaging system be on your ability to detect some of these smaller structures if you have this, very large discrepancy in the critical, what you're finding experimentally versus the model, right? Could there be some underlying structure that you're not detecting the onset of that due to the limitations of your resolution and the fact that you are trying to do it with your own eyeballs?
Yes. So first part, I haven't done it, but there has been some work in the literature done basically using a contrast adjustment like this for these bottom images. And just to the eye here, there's no instability here, but here there's all this stuff going on in the middle, and we can pick that up with edge detection. I haven't quantified that. There would be a way to kind of.
But you're limited by your line pairs per millimeter, right?
So
so you cannot make a comment below the imaging resolution of your system.
With this system, we have a lower resolution than what I talked about earlier, that 20 microns. For this one, I would expect it to be probably 5 times less resolved, maybe even more.
So if you could resolve lower, let's speculate, right? Hypothesize that maybe there is some structure there that you're detecting way too late, right? In the expansion of this process. If some other structure was there, that could potentially bring your measurements of the onset into line with the models, correct? Is that true?
Yes. Yeah.
Well, but look at the difference. Show a typical difference between the model and your prediction.
Yeah.
And this is based on RC, not the flame thickness. So RC, pretty well within a millimeter scale, right? Out of 5 centimeters or whatever. So it's actually a much bigger difference than the resolution thing, right?
Especially with the hydrodynamic instability, because it's density and we're using Schlieren, so we're actually looking at density with Schlieren. I think Schlieren is the way to go for detecting onset of instability. This, like you said here, the model is over predicting. We're getting an onset of maybe 1 or 2 centimeters, and the model's saying 10 or 12.
Okay,
centimeters.
I saw, okay, I forgot the difference there.
So yeah, I think.
Do you think you could see then the other instability that you mentioned from the other pictures on the bottom left corner of your examples, the thermal one, the diffusive one,
Yes.
right, which had a much finer structure? Can you resolve that with this system?
Yes. Yes. So in the same way that using that edge detection would pick up all of those wrinkles, it's going to look the same with this one. The tricky thing is that this instability sets in. That instability sets in very, very early. So it's so small. The flame's really small when it happens. So that's the case where I don't think we could resolve the onset of that instability with this system. But it also happens from the very beginning of flame propagation.
Can I ask another question from Zoom again? Isn't that, looks to me like a standard cellular flame instability? And you just called it those wrinkles. Is it not the cellular instability?
It is the cellular instability, yes.
There's a lot of work that's been done on that, both computations and measurements of this in methane. So I think there's something to compare to, unless it's a different regime.
These,
Mhm.
yes. I looked at syngas with this. So this was hydrogen and CO with CO2 and helium. So diffusionally, we're in an entirely different place than we are with methane, I think. But when we talk about the cellular instability, I think for this video, we're talking about top right, right?
Yeah.
Bottom, what we were just talking about with Dr. Cooper, the bottom left is more of a thermal diffusive instability. And I think that is entirely a cellular instability because it's on a molecular scale. The cells, I'm not really sure if they're a cell. It's much, much smaller than that.
But thermal diffusive instability is one of the things that leads to cellular structure, isn't it?
It plays into it, yes, yes. If we have thermal diffusive instability, the cells will form earlier, but they are hydrodynamic cells, at least to my understanding.
Thank you.
Yes, thank you. I've seen your test rig 2 or 3 times, but I still don't necessarily understand what I'm looking at here. So this through the window of the bomb, right? Yeah. And we've got a sparker. Is that what that is?
Yeah.
So it's basically like a spark plug.
Long spark plug, yeah. Okay.
And then on slide 39, you might shoot into that real quick.
Yeah, on my way.
Is that probe going in the same thing? It's just different angle?
Yeah. Yeah.
That's all. Thank you.
I'll show you more later.
Any other questions? All right, so at this point then we'll have to close the session then. We'll have to ask the audience, the general audience to they have a place to go. Bring it to a room or they can go on a lab tour. Okay. You guys want to discussion? Yeah. Why don't you take it to okay, let's have more of this. If they want to go on a tour, good. That'd be steal your thunder, but it'll give something to do. They have to. Sure. Yeah, let's do that now.
Yeah.